Okay, let's start the training. I would like to remind you that we cannot unmute the participants. We cannot turn on your microphones and take loud questions. If you have a question, you can write your questions into the Q&A box, please. Please do not type your questions into the chat box. Just use a Q&A section. Now I ask Dr. Özcan Dülger to begin the program, parallel programming with Cuda. Please, dear professor.
Thank you so much, dear Saide. Hello, everyone. My name is Özcan Dülger. I am visiting assistant professor doctor at the Department of Computer Engineering in the Middle East Technical University. And I'm also assistant professor doctor at the Department of Computer Engineering in Artvin Çorum University. Today, I will give you a training about the Cuda programming language on the GPU. Let's start our training. Okay. This training will be separate to the 2 days. In the first day, I will show you the differences between the CPU architecture and the GPU architecture. And I will also compare the differences between the threads of OpenMP and the threads of Cuda and their behaviors. Then I will start to the basics of the Cuda programming language. Then at the end of the first day, I will give you an example problem, which is about vector addition. I will give you some time to solve this problem. Then I will show the solution of this problem. Let's start with a quick review to the Van Neumann architecture. This is the basics of the processors. In the Van Neumann architecture, there is a CPU, central processing unit, and a memory, a separate memory. In the central processing unit, there is a control unit, arithmetic logic unit, and the registers. Here, in the control unit, the instructions of the programs are executed, and if there is an arithmetical or logical operations, the arithmetic logic unit will be active, and during this process, during these calculations, if there's a temporary data, it is stored in the registers. For the memory, the data of the program and the instructions of the program are stored in the memory. Okay. Let me show you a simple example here. We have a program and it has many instructions. These instructions are executed on the central processing unit in a serial way. Here, more than one program can be executed simultaneously, but still it is a serial execution. The instructions of program can be executed in a random fashion on the central processing unit. And later on, a single processor is not sufficient for the computation of the programs. And the multi-core processors were provided, and these the processors share a single memory here, as you see that. So more than one program can be run in different central processing unit at a time, and it was extended to the many cores. Here there are 8 cores. This is 8-core multiprocessors, and later on here there were new paradigms, new APIs invented to be able to use these multiprocessors at the same time. I will show you the basics of OpenMP API. Here, I would like to show you that we have 4 distinct programs, and if we execute them in a single core, still the executions are serial. So we need to distribute this program to the other cores. Still, if we if we execute 2 of them in a single core, and the remaining one another single core, is not sufficient because we have more than 2 processors here. So this is the best approach for us. On the other hand, we can also distribute the instructions of a program to a different processing units here. There is a single program, and we want to distribute the instructions of this program to the different cores, and our aim is to execute that instructions at the same time.
Dear Professor, we have a question. In today's program, do we know the GPU in our computer or run the examples?
Yes, you need a GPU environment for the problem that I will give at the end of this lecture. I announced it before on the website of the training. So you need to have a GPU environment. But I will also show the solutions of the problem. You can also do it later. You can also solve it at home and check your solution with my given solution. Okay. Okay. In order to use the many cores efficiently, we have a programming API. OpenMP is such kind of API, and that supports shared memory multiprocessing programming in C, C++, and Fortran. And with OpenMP, we can distribute the instructions of the program to the OpenMP threads, and these threads run simultaneously on distinct cores. And there is a default thread in OpenMP which is called as master thread. Okay, now when we create our program, there is a default thread which is master thread. In here, there is a single thread, and it is assigned to a single core. This is also a serial approach. So in order to run the threads in parallel, we must create more than one threads. Here we create 4 threads, including the master thread. But again, still, all of the threads are executed on a single core. Still, it is a serial approach. Why? Because we must distribute these threads to the distinct cores. How we can do it with OpenMP here? This is our aim. we try to distribute them to the distinct cores. So these all threads run in parallel. How we can do it? There is here an environment variable here, GOP CPU affinity, which is about affinity. When we set it here as 0, 1, 2, 3, that means assign the threads to these cores. What I mean, the zeroth course, this one, the zeroth course, the first course, second and third core. So if we set their index to this variable, all of them will be active and the threads are distributed these cores evenly. So this variable, environment variable is important. Otherwise, all of the threads are executed in a single core. Before showing examples, I would like to show you the specifications of my processor that I used in the examples. This is a 4th generation Intel Core i7, and it has 4 cores, and its frequency is 4 gigahertz, and the size of its memory is 16 gigabytes. So we have 4 physical cores in this processor. Let's start with the examples about OpenMP and continue with the Cuda. Here in this example, we have an array and we assign some values here, as you see. There are 3 multiplication operations and read-write operations from memory. So it may take too much time. And the size of this array is 225. And in the second for loop, we do some calculations, as you see that both the CPU and memory are very busy in these operations. And when we run it serially without using OpenMP, when we run it serially, we obtain 1.06 second execution time. And we will compare it with the results of OpenMP and Cuda. And in our second example, here we set the number of threads 4 and we distribute the workload of this second for loop, distribute the workload of for loop to the threads evenly. Here, this pragma tells us OpenMP pragma, this is an OpenMP pragma, and with this pragma, the workload of for loop is distributed among the threads. So when we run it, before that one, if we set the affinity to 0, that means only the zeroth core is active. Here we obtain 1.15 second execution time with 4 OpenMP threads. This is also worse than the serial implementation. So as you see that this is not the true solution, true approach for us. If we set the affinity to 0 and 1, that means only this 2 of them, the 0 and first core, will be active, and these 4 threads are distributed among these 2 cores. So as you see that we obtain around 2x speed up with the previous example, but still is not a true approach for us. What should we do is set the affinity between 0 and 4. That means all the cores are active and the threads are distributed to this course evenly, and we obtain here 0.29 second execution time. So it is about 4x speed up. We obtain 4x speed up. This is what we aim, because we increase the number of threads from 1 to 4. So our aim is to obtain 4x speed up. So this affinity is important. So do not forget to set this variable properly. Okay, let's continue with another example. Here is this is a serial code again. We have 3 arrays, A, B, C, and we assign some values with the first loop. And we do a multiplication and set the result of this multiplication to the array C. And in the third loop, we use the actual value, latest value of array C. Sorry. If we examine this course carefully, as you see that once this loop is execution, the second one, this one will continue, but here the latest value of C array, the latest value of C array are accessed in this for loop. So the execution of this for loop must be completed before continue with the next for loop. In the serial version, this is not a problem because all of the loops are executed in a serial way. But in parallel environment here, there is a problem. Let's look at what is the problem. This is again an OpenMP code. Here, this is an OpenMP instruction, and inside of this this function here, inside of this function, we can use the instruction of OpenMP, and the threads are created here, and we can access all of the threads inside this fragment. So let's look at the problem here. Again, this for loop is distributed to the threads evenly. And the second for loop is also distributed to the threads evenly. And there is a no wait clause here. That means when a thread completes its job here, continue with the next for loop immediately. We have 4 threads, and any thread that completes this for loop should not wait the others to complete this for loop. So once the thread completes its job in this for loop, it continues with the next for loop immediately. So when a thread completes this for loop, and execute this for loop, it will access to the array C. And we need to access to the latest value of array C, but maybe the latest value of array C has not been calculated yet. What I mean, when a thread access to this array, the other thread that executed the same index of the C array may not be executed yet. So we cannot access to the latest value of C. Be careful about the index of the C here. the first thread executed the first index of C array. In this example, the first thread executes the last element of C array. So be careful about it. Which the fourth thread, the last thread, update the value of the last element of C in this for loop. The last thread update the value of the last element of the C array here. So the results will not be stable when you run this code. How we can overcome this problem? We must put a barrier here. A barrier is a good solution, or a synchronization between the threads must be obtained between this for loop in order to avoid unstable results. So one solution is a pragma here, again an instruction of NAMP instruction. We can write a barrier here. So all of the threads wait here until the remaining ones completes their job in the for loop. And all the threads reach to this point. The threads continue with the next instructions here. So we can ensure the stable results with this approach. In the second approach, there's a no wait clause here. We can remove it, and we remove the no wait clause. There will be an implicit barrier here. That means when all the threads complete their job in this for loop, they will continue with the next instruction. So that when a thread completes its job, it will wait for the other threads to complete their job. This is another solution in OpenMP. And the third solution is we can use a global variable, which is complete count. Here, all of the threads access to this global variable. And here, we use the while loop here. This condition is when the complete count, the completed threads, the number of completed threads is equal to the number of total threads. This while loop will not be satisfied and will not block the threads in this instruction. There is a critical point here with OpenMP. That means only the one thread can compute this instruction at a time. So when all the threads complete their job in the for loop, the value of complete count will be equal to the value of the number of threads. So this is also another solution for this instability problem. Okay, let's continue with Cuda programming. Before that, I would like to check the questions. Okay, there is no question here. Okay, let's continue with Cuda programming. It is a platform that runs with C, C++, and Fortran programming language on the GPU, and it enables the functions running on the parallel on the GPU. It works on NVIDIA GPUs, and its behavior is single instruction, multiple thread behavior. Here, This is an architecture of Tesla K40 board that I use in my examples. Here there are streaming multiprocessors in K40 board. There are 15 multiprocessors here, streaming multiprocessors, and they have many cores in their architectures. And there is a two cache. The streaming multiprocessors share this R2 cache, and there is a memory access point that enable us to plug in the memory, the external memory, to our GPU board. Let's look at the streaming multiprocessor in detail here. This is a streaming multiprocessor. As you see that there are many cores here in K40 board. There are 1,092 cores, single precision floating point years, and there are 64 double precision floating point units, and 32 spatial functional units that is used for the spatial functions in mathematical operations. And there is 2 load store units that is like the registers in CPU. The temporal variables are stored here. And there is an I1 cache and shared memory where all the cores shared this memory. And there are 4 warp schedulers in this architecture. The main important point for us, it has 192 cores. And this is a general illustration of GPU architecture, 15 symmetric multiprocessors, there's an R2 cache, and there's an external main memory. And there's an important concept in Cuda. This is called warp. Warp is a hardware concept. We cannot access it by writing a code in our program, but we can access it in an indirect way. It's an hardware concept. It consists of 32 threads, and the warps are scheduled to the streaming multiprocessors instead of threads. And these 32 threads in the warp are physically related to each other. They are physically related to each other. What this means is for any warp, in order to finish a warp its job, all the threads in the warp must complete their job. So when all the threads complete their job in the warp, the job of warp is also completed, and another warp are scheduled to the course. I will show you, and I will show the examples about it. This is an example instruction here. 3 memory operations, 3 arithmetic operations, and 1 spatial function operations. So all of the threads must complete these operations, must calculate these operations, and the warp will complete these operations. The warps are scheduled to the course here. Since a streaming multiprocessor has 192 cores, at most 6 warp can run on a streaming multiprocessor at a time. We can run 6 warp in parallel in an essence, and the other warps wait for the warp to complete its job. And I will show you differences between GPU and CPU architectures. CPUs are latency-oriented, has latency-oriented cores. GPU has throughput-oriented cores. So in CPU, there is a large local cache. This enable us faster executions, faster memory loss for operations, and there's a sophisticated control unit, and there are small number of registers and single instruction multiple data units. But in GPU, the throughput is important. So the local and cache memory is not large as in CPU, but the registers are large than the CPU because we have many cores in the GPU, and each core need to have its own register, and the number of cores is very large. The number of registers should be very large, and it has a larger single instruction multiple data unit than the CPU because of many cores on the GPU. So if we compare the latency oriented and throughput oriented, there is an example here, a good example. Let's we have a car with the capacity of 5 passengers, and the average speed is around 300 kilometers. And this we have a bus with the capacity of 40 passengers, and the average speed is 100 kilometers. So let's assume we want to arrive a location that is far away from us, around 300 kilometers. It is 300 kilometers far away from us. So, and we want to carry 50 passengers to that location. With the car, on each arrive, we can carry 5 passengers. So, in order to carry the 50 passengers, we need to arrive at least 8 times to the location. So it takes around 15 hours to carry the 40 passengers with the car. But with the bus, we can carry all of the passengers at our first arrive. So it takes around 3 hours. So when we compare it, we do the same operations with latency-oriented architectures and throughput-oriented. There's around 5x differences. So this is the powerful property of GPUs over CPU. And let's look at quickly to the properties of the CPUs. As I said before, there is a sophisticated control unit. That means there is a branch prediction for reduced branch latency, data forwarding for reduced data latency, and it has powerful arithmetic logic units. It reduces the operation latency, and it has large caches. So enable us to read and write operations faster. In GPUs, there are small caches here. It is used to boost the memory throughput. And there is no branch prediction, data forwarding. It has a simple control. So you cannot run any code on the GPU because of these properties, this hardware of GPUs. I will show you what kind of problems can be executed on GPUs and what can be executed on the CPUs. So there is no branch prediction, data forwarding, energy efficient arithmetic logic units. And of course, we require massive number of threads to tolerate the latencies. So in order to benefit from the GPUs, we must create many threads in our program. And let's contribute programming concepts of Cuda. In a programming concept, this is not a hardware concept. We have a grid, and the grid consists of many blocks. And inside the blocks, there are many threads. They share the shared memory inside the block, and all of the threads have their own registers. And these blocks access to the global memory of the GPU. The blocks are created in a grid, and if the threads are created as blocks in CUDA programming, each thread has a unique register and thread ID, as I said before. There's a shared memory for the threads in the block. All the threads inside the block can synchronize each other, but the threads across the blocks cannot synchronize. So they are in different blocks. They can only access to the global memory. The blocks are distributed to the streaming multiprocessors evenly. They are distributed to the streaming multiprocessors evenly. And threads are executed on the course as verbs. Verbs are scheduled to the course, and the threads inside the verbs are executed on the course. As I said before, verb is a hardware concept. We cannot create it in our program, but we can control it indirectly in our program. I will show it. Cuda kernel is a function that runs on the GPU, and the blocks in a grid execute the same kernel, and all the threads in the blocks complete the execution of this kernel. The execution of this kernel is also complete. Let's start with a small example here, a short example. This is a CUDA kernel. We must use global keyword here. This is CUDA kernel. This is a function runs on the CPU, not on the GPU. And here in our main function, at first we call the function runs in the CPU. Then we call our kernel, and this kernel are executed on the GPU here. We create one block and one thread. So there is a single thread here. And the output here, hello over CPU and hello over GPU. When we want to compile our program, we can use EuroCC. This is for a Linux environment. Let's continue with here to the kernel. If we have a variable is allocated on the CPU, memory of the CPU, we can pass this variable as the parameter of the kernel. And we pass it to the parameter of the kernel. There will be a memory location is allocated on the GPU for this variable. Since this is a single variable, it is allocated on the register of the thread on the GPU. But this variable is allocated on the stack region of the CPU. So we can send it as the parameter of the kernel. Okay. Here in this example, we create 2 blocks and each block consists of 32 threads, so 64 threads in total. And the output is like this one. For 64 threads, execute this command. We can also use a built-in variables here with type of DIM tree. This is special type on the GPU. So this means this represent number of blocks and represent the number of threads in the blocks. And we use these variables here in our kernel. Still we get the same result here. So and the dimension of these variables can be 1D, 2D, or 3D. In the 1D version, we create 2 blocks with 32 threads. In the 2D version, we create 4 blocks here, 4 blocks. Each block consists of 16 threads. And in the 3D dimension, we create 8 blocks, and each block has 8 threads. In total, all of them has 64 threads, but the difference is the number of blocks here. But the total number of threads are equal. In the following examples, I will use 1D dimension. These are the built-in variables. This is for dimension of the grid, X dimension, Y dimension, and Z dimension. This is the dimension of the block, X dimension, Y, and Z. These are block IDs is the index of the block in the grid. Thread IDs is the index of the thread in the block. We will use these built-in variables on our examples. And these can only access inside the Cuda kernel. Let's print them. Let's print the built-in variables here inside the kernel. This is the ID of block. This is the ID of threads in the block. And we create here 2 blocks. Each block consists of 4 threads. So we have 8 threads in total. Let's examine the output here. It is printed here block, first block with the 0 thread, first block with the first thread, here 0 block with the 0 thread, 0 block with the first thread, and so on. We can print them here, but what about we want to obtain global thread ID? These are, as you see that, these are local thread IDs. These are the index of the thread in each block. But now we want to obtain the global ID of thread. That means the index of all the threads in the grid should be distinct, should be unique. That means here, starting from 0 to starting from 7 here. So they have unique thread ID, as you see. How we obtain this global thread ID? Here in this example, we have 8 blocks, and each block has 64 threads. Here we have 8 blocks, and these are the local thread ID of the threads inside the blocks. They are starting from 0 to 63. But we want to obtain here these global thread IDs. The first thread in the first block starts with 0, and the last thread of the last block must end with 511. So how we can obtain it is the formula here. This is the formula. Let's check this formula. Here, block dim.x is the block size. That means the number of threads in the block. It is 64 in our example. And multiply with it with the index of that block. Index of that block. It is between 0 and 7 here, as you see. And the local index of the threads in the block. And it is between 0 and 63. If we use this formula, we get the global thread ID. And when we print down here, we obtain the global thread ID in the code. And in the third parameter here, we print the value of global thread ID. And as you see that, they are started from 0 up to the 7 in our example. Okay, now let's continue with example in the OpenMP. Let's do the same thing with GPU. Remember that in our example, we have a for loop here, and we distribute the workload of for loop to the OpenMP threads evenly. Here, let's try to run it as a serial way on the GPU. We have a compute Cuda kernel here, and we call it here with one block and one thread. That means we have here we create only a one Cuda thread in this example. And we run it on the GPU, we obtain 86.8 seconds. When we compare with the serial version of this code on the CPU, it is 1.06 seconds. So this is a terrible result for us. As you see that creating a one thread and run this for loop in a serial way is not a good approach on the GPU. So we need to change our aim, change our approach in order to solve this one. Because there are many cores on the GPU, but only a single thread is active and executed on a core. The remaining cores are idle. And also the frequency of CUDA cores is not as good as the frequency of a processor on the CPU. And in the second approach, we can try to distribute the workload of for loop to four CUDA threads, like in example 2. Remember, in example 2, we create 4 threads and we distribute the workload of for loop to these 4 threads by using OpenMP. Here, we create 4 threads, 4 CUDA threads, and here again, we distributed the workload of for loop to these CUDA threads. So still we get a terrible result here. Even if we have an improvement by comparing the previous one, 23.1 seconds is not a good solution, good results for us. But if you remember that we obtained 0.29 second execution time with the OpenMP version. So this is also not a good approach. Here, if we remove for loop is not suitable to run on a GPU explicitly. So if we remove this one for loop, and if we create a thread for each iteration of the for loop, for each iteration of the for loop, we create a Cuda thread. Remember, the size of the array is 2/25. So we create 2/25 threads, and each thread execute each iteration of the for loop. Now, if we execute our CUDA kernel with this approach, with 2/25 threads, here we obtain 0.005 second execution time. This is very incredible for us when we compare it with the results of OpenMP. Remember, it is 0.29 seconds. But here, this is the correct approach for the CUDA programming on the GPU. Let's continue with the another example. Remember, again, example 4. There is a dependency. Remember that there's a dependency between this instruction and this instruction because of the C array. So let's try to solve it with CUDA programming. If we use a single CUDA kernel, and if we execute them in a serial way for each thread, we also face the same problem. The results still are not stable because this value may not be the latest value of C. When a thread access to this value, it may not be the latest value of C. So there should be a barrier between this instruction and this instruction. There should be a synchronization here. Let's try to do it with OpenMP. How we can solve it here? We can use synchronous instruction, but still the results is not stable. We cannot overcome this problem because sync threads instruction is only valid for the threads in the same block. So the threads in the same block are synchronize each other, but the threads across the blocks cannot be synchronized with this sync threads command. So this is not a solution. Let's try to do a while loop here as in the OpenMP here. Let's try to do this one, but it's still not overcome this problem. Why? There is an infinite loop here because of the while loop, because of the condition of while loop. Let's examine the condition of the while loop. There is a global variable here, again, complete count. All of the threads can be accessed to this volume. And there's an atomic operation here. We increment the value of this global variable here. But in the condition, this condition is always satisfied because the number of this global variable will have never been equal to the number of threads in the grid or the size of the array, because some of the Some of the blocks waiting on the queue to schedule to a streaming multiprocessor. Not all of the blocks can assign a multiprocessor at a time. Some of them you must wait the others to complete their job. But because of this value, there will be no any block that completes this Cuda kernel, because all of the blocks will face with infinite loop. So the waiting blocks cannot be assigned to the streaming multiprocessor. So the value of complete count will not have been equal to the value of size. So this is a good solution in OpenMP. This is also a good solution for OpenMP, but it is not a good solution on the GPU. So this is the correct approach here. This is the solution. What we do, we distribute this compute kernel into two independent Cuda kernels. And there is an implicit barrier inside the Cuda kernels. There is an implicit barrier inside the Cuda kernels. So once all of the threads complete this execution, the next Cuda kernel will be executed. So the threads will access to the latest value of C. This is the correct solution. They use the implicit barrier between the Cuda kernels. So the Cuda is very suitable and the number of data is very large, and the same instruction applies to full data. So, and for an efficient application with Cuda, we must avoid nested if-else structures, large number of dependencies between instructions, nested for while loops, too many synchronizations across the blocks, and non-coalesced access patterns on the global memory, and assigning different types of instructions to different threads. So in this case, Cuda is not suitable for us. Let's continue with let's continue with the memory operations. Here, this is a function on the CPU. We have an array here. Its size is 1000. We assign values here, and we print by using this function, and we delete it. We free the memory location of this array. This is a serial code, and I will show you the GPU version of this code. Let's examine the GPU version. Here again, we have an array with the size of 1000. And this is our Cuda kernel. We still print the value of A as in here, as in this function. So as you see that the for loop is removed here, and each thread executes to each index of each iteration of the for loop. This is our global thread ID. The number of threads in the block is 64, and the number of blocks in the grid is calculated with this formula. I will explain this formula. We have a host array with the size of 1000. We assign values to this array. Now we have a pointer for the array on the GPU. With Cuda malloc operation, we allocate a memory location on the GPU for this variable. Here, let's explain the details of this code. It has two parameters. The first one is the address of the memory location to be allocated. And the second one is the size of the memory location in terms of bytes. So in here, the address is here, this pointer. Yeah. The address is stored in this pointer, and the size is here, size of int multiply with size. Since this should be a byte, we multiply size with size of int instruction. And CudaMap CPI, there is a CudaMap CPI. We are trying to copy the data from CPU to GPU. Let's look at the parameters here. The first parameter is the destination, that is the address memory location on the GPU. The second one is the address of the source, that is the memory location of the CPU that we want to copy to the GPU. And the third parameter is the size in terms of bytes, the size of the data that is copied in terms of bytes. And the fourth parameter is the transfer direction. It can be from CPU to GPU, from GPU to CPU, or from GPU to GPU. The fourth parameter is related to the transfer direction. And we create our variables with type dim3 here. And we call our kernel with this dimension 17 blocks. Each block contains 64 threads here. And we copy the result to the CPU, copy the result from GPU to CPU. When we switch the first two parameters here, we copy the results of GPU to the CPU, and the fourth parameter should also be updated here. It should be now device to host, or the memory copy operation from GPU to CPU. And at the end, we free the memory location of the array on the CPU, and with Cuda free, we free the memory location of the array on the GPU. And here, we set this. We set the size of the block to 64 because since the number of threads in the warp is 32 and the warps are scheduled to the course, it is important to set the number of threads in a block to the multiples of 32 is important in order to use the resources efficiently. And here, with this formula, as you see that we create 16 blocks rather than 15 blocks. If we not add plus here, add 1 here, we can create 15 blocks, but it is not enough to manipulate our data because the size of the data is 1000. So we must add 1 here. So we will create 16 blocks. But but there is a important point here. When we create 16 blocks, we will create 1024 threads here. 1024 threads, but our size of our array is 1000. So if we don't use here, if close here, 24 threads face with out of bound error because the size of array is 1000, but we create 1024 threads. So 24 threads will face out of bound error. In order to overcome this problem, we can use here an if clause, and in its condition, we bound the global thread ID to the value of size. So we will not get an out of bound error in this situation. There are some variable types on the Cuda. A local variable, it is allocated on the register and can be accessed by its thread, and it is destroyed when the thread is destroyed. And we have shared variable. So it is a shared memory variable, and the threads in the block can access this shared variable. And when the block is destroyed, this shared memory, shared variable is destroyed. And we have here global variable. It is allocated on the global memory of the GPU, and its scope is great when the application is terminated. This variable is also destroyed. And it is also same for constant variable. There is a note here. The arrays created by the threads are allocated on the global memory, not in the register. When a single element variable that is allocated on the register, but if it is an array created by the threads, they are allocated on the global memory. Here an example of defining the shared variable here inside the kernel. By using shared keyword, we can define a shared array here, and all the threads in the block can access to this shared variable. As you see that here, with their local thread ID. And so if we need to obtain the latest value of this shared array, we can use a synchronization here, a synchronous instruction here. So this ensures us that we will obtain the latest value of shared variable. So we can synchronize them here. Okay, I mentioned it. This is the Cuda execution model. We have a serial code. When we call a Cuda kernel, many threads are created and they are executed. When they finish their job, we continue with the next instruction on the serial code. Then again, if we call a Cuda kernel, many threads are created again, and so on. This is the Cuda execution model. There are some blocking, non-blocking functions. Blocking means there is a implicit barrier between the Cuda functions here. These are Cuda malloc, Cuda memcpy, Cuda device synchronize. And all of the threads complete execution these functions, the program continue with the next instruction on the CPU. But in non-blocking functions, non-blocking functions, Cuda kernel, Cuda malloc is a synchronized version, but a synchronized version of Cuda memcpy and so on. So the program does not wait to complete that operation on the GPU and continue with the next instruction on the CPU immediately. So the program does not wait in these functions. And okay, thank you. And we will continue with the example problem. Now I will upload it in a couple of minutes. You can access to the files of the example problem. There is an explanation file and there is a program, but some of the parts of that code were removed, and you will write your code in that Cuda file. So let's have a 10-minute break, and I will upload it during this duration. Let's continue at 3 p.m.